Hello class, today we're going to focus on section 20.1, the slope of a curve. To frame this lesson, we're going to focus on the function f of x equals x squared. And here's that function. I grabbed this from Desmos, and you can feel free to do the same, but we're going to use this as reference in this whole lesson, at least to start. Let's consider two different points on this curve, and let's just say one point is point P. I'm going to pick it arbitrarily. And point Q somewhere else on this curve, again, just randomly picked. Now what if I asked, what is the slope of line PQ? I want you to take a moment and actually think about how you would actually write out some theory or design on how you would answer this question. Okay, so let's get started. As a reminder, what is slope? Well, we can write this as m, but this is the change of y over the change in x. We can rewrite this as y final, or yf, minus y initial over xf, x final, minus x initial. Another way of writing this would be y2 minus y1 over x2 minus x1. Now these are all formulas to help us understand what slope is, but if we were just referring to what slope is in words, would be to say that the slope of a curve is the steepness of a line. So how does that look graphically? Well, if we go to our graph and we actually draw a line here connecting these 2 points, we would say that the slope is not a straight line. So we're going to undo that and try it again, try to have a steadier hand, but we want to connect our points P and Q, and I think that's a little bit better. So we want the slope of this line, aka what is the steepness of this line here between points P and Q. And as a reminder, we picked P and Q, and it could have been any selection of P and Q, and it was arbitrarily picked. Now I'm going to try to select this area and see if I can move it without changing the size. Let's try that again. Okay, there we go. I think I got it now. In this case, I could have moved Q closer and closer to P. Well, in this case, if we're going to refer to Q being arbitrary and that it is just any value to P, we can actually rewrite or redefine what Q is. Let's say we define P as 0.11. I'm going to go to my graph now and actually fix that, and looks like I got my line a little screwed up, but let's just set that up correctly. Yeah, it's close enough. And in this case, I'm going to do 1, 1, which will be right. 1 will be halfway, so this should be point P down here. So we consider P to be 1, 1, but remember, Q can be anywhere. So we can just say, well, it's some difference from P, so Q we're going to define as, well, your x value is going to be some increase of from 1, so we're going to say 1 plus h. We'll define it as that. And understand for this function, again, this function is f of x equals x squared. So when any value we have for our x, we have to consider that squared for our y. So with our 2 points, let's plug this into our slope formula. Taking a moment to just really practice this, because remember your variables will be tricky if you don't do this appropriately. In this case, I've plugged in my y2, my x2, my y1, my x1. Now we're going to simplify this further and say that in this case these will cancel out, and you're left with a setup of the following. This is now equal to h squared plus 2h plus 1 minus 1 over the whole thing, which is h. You should notice that now these two are going to cancel out, and you're kind of left with, so not kind of, but you are left with an h, if I factor this out, h plus 2 over h. And these values will not cancel out, and you're left with, actually let me just do that one over, make that red, there we go. And we're left with h plus 2 as our final answer for this. So what does this really tell us? This is more of a focus on that this here is the slope for any value of h. So here's where it gets a little bit confusing, is to say, before, when we've taken the slope of any 2 points, we've considered a point here and a point here, some distance away, and we were able to take this line between those 2 points, this line, and saying what is that slope of that line. Now, the problem with this is, what if I ask a different question to state the following? Now, in this case, I write, what is the slope at point P? Well, what makes this different from what we've been saying before is we've considered point P and point Q. But now if we're considering just point P and we wanted the slope of that singular point, that changes things a little bit. We have to consider that there is a singular point, not 2 points. Now, since H here H was written in purple, let's keep it purple. Since H represented your difference between point P for X and Y, we're kind of saying then if it's the singular point that H is actually equal to 0. Or, as talking about limits, approaching 0. So I'm going to rewrite that as the following. That the slope of the curve at P is equal to the limit from Q to P slope PQ. And I should say rather that it's the slope of line PQ. That's what this line means on top. So that's all well and good, but how does this here apply to this? Well, since this is the slope, and we're saying we're taking the limit from Q to P for the slope PQ, which is this, we have to say that this is that we're taking the limit of this here. So I'm going to rewrite that now. So the limit as H approaches 0, remember that's the difference between Q and P, for 2 plus H is equal to just simply 2. Another way of writing this is saying, therefore, the slope of the curve y equals x squared at P point 1, is 2. So let's consider this next question of saying more generally finding the slope of the curve y equals x squared, which we've been doing, but now instead of point P being 1, we're considering any point, being extremely general, saying x is our input, x squared is our output. So let's consider how we find the slope, which is the slope of PQ. Remember, we're still considering this general PQ, right? Is going to be equal to now x plus h squared minus x squared over h. As a reminder, remember h is going to be our change here from p and q, which is ideally going to be 0. So if we were to write this out, we would get, this case, x squared plus 2xh plus h squared minus x squared over h. Now, you might start seeing a pattern here of binomial theorem, but we'll get more to that later. Let's simplify and reduce. So in this case, the x squareds will cancel out, and you're left with 2xh plus h squared over h, and again, we're going to factor out an h, so let's continue over here on the left, and we're going to have h, 2x plus h over h, and these we're going to cancel out. And we're left with 2x plus h. Now, to find the slope, we're going to need to say that the limit, or take the limit of this whole bit, because remember the limit here is going to be as q approaches p, which is equal to the limit of h approaching 0, because that's the difference between them. So the h approaching 0, let's apply that to this slope here. So we have the limit as h approaches 0 for 2x plus h. And what do you end up getting? Well, just simply 2x. So what does this mean for us? Well, we generally said for any point along y equals x squared, because that's what x and x squared is just taking your input and squaring it, it's going to be 2x. And if you actually look back at your old one, we said that point was 1. Well, if you plug in 1 here, you're going to get the slope equaling 2, which is what we had before. So this here is what we do to find our slope of any single point. We can actually generalize this theorem with this specific notation, whereas we do f prime, that's our notation for finding the slope of a point, with the limit as h approaches 0 for f of x plus h minus f of x over h. And this is huge. This is actually your derivative. We will commonly refer to taking the slope of any single point as this derivative. Make sure that this all here is in your notes and you understand how each part functions. We're going to go through a few more examples on how to simplify this process because it is a bit tiresome to do this every single time. Alright, so let's apply our newfound formula for this. So we have to start off with our limit as h approaches 0, or as a reminder, remember h is the difference between the 2 points. And then we're going to have x plus h, remember that is your added difference, to the 5th minus the initial, which was x to the 5th, over, in this case, we're going to have simply h. Now you might start feeling afraid because you're looking at this and saying, oh my god, I have to do this out, this is scary. And then my response would simply be using the binomial theorem. Okay, enough of that silliness. Yes, the binomial theorem will work for this. So don't worry about it, you can do it, and I know you can. And so I want you to try and make an attempt before I post my work. So your first step, you should have utilized your binomial theorem to get this set up here, and then still setting it up with this minus x to the 5th. Notice that these two are going to cancel out, and you're going to be left with this setup below. Also stating that with this setup you have a common h that's throughout. So I'm going to simply factor these out. That gets canceled. That becomes a 1. This becomes a 2. This becomes a 3, and this becomes a 4. So we continue writing this out. We'll start off with our limit here. And we have this set up here. And if you notice, we have nothing stopping us from applying our h to the 0. Before we did, because it was in the denominator, but no longer do we have this issue. So now we can just write this out again with the application of the 5x to the 4th plus 10 x cubed times 0 plus 10 x squared times 0 plus 5x x times 0 and 0, all equaling the final answer of 5x to the 4th. And that is our answer for this. Now you must be saying, there must be an easier way, Mr. DiTieri. There must! Well, you'd be right. And for all you naysayers, they say, well, if there's an easier way, that means we don't have to do this whole setup. You'd be wrong. You will be assessed on how this will be done, and actually it's a neat way to see how this process can be done from point A here, applying the limit to your slope, all the way down to this simplified answer. Another way of doing it is actually, you can quickly see this as an answer to say f of x is equal to x to the 5th and f prime of x is equal to 5x to the 4th. And I'm going to show you that with a theorem. The theorem states if we consider f of x equals x to the n, that actually f prime of x, or the derivative of it, is just simply going to be n. So you bring the exponent down to multiply your function, x n minus 1. So this is your simplified theorem for all of that, all of this. Okay, let's apply this to another one. So we now consider this other one here saying your function's 3x to the 5th. I want you to apply our new setup to this and see what you end up getting as just some sample. Okay? Now, you may have gone through the long process of writing the limit of this function. Now, if we apply our latest theorem, we can actually state that this f prime of x is actually going to be equal to 5 is being brought down, multiplied by 3x, now raised to the 4th. Our constant is left there because it can be pulled out of our function and just held as a constant outside of it, and we can actually say now this is equal to 15x to the 4th. See, much easier. Alright, let's consider two more ones that are slightly more difficult. And here are those two. Now I'll give you a few pointers from the beginning is to say that these can be taken as separate functions that you take the derivative of and respectively add or subtract them together. Similar to this one, but you have to understand again what these exponents are and what they refer to. So feel free to apply our newfound theorem to this and see what work you get. And here's a look at some of my work to say that we set it up as your derivative of this function, considering that you're going to bring down your exponent here, multiply it to our constant, and make sure you're decreasing the initial exponent from 2 to 1, and so on and so forth, getting a final answer of 24x minus 4. Remember, that's a generalized derivative, or slope of the curve, not a slope at a specific point. You can pick any point for x and plug that in to get your slope at that point. And here, we're going to do this for a slightly more difficult one just because we have, fractional exponents to consider. This is to negative 1/2. Remember, that's what we have here. And we have this one here. I already had squared in the denominator, so I just simply said we're going to minus it further, and if we minus it further, we have an increased negative exponent, meaning, we have an increased denominator exponent. So this is going to give you negative 7 times the negative 2, because originally, remember, it was 2 in the denominator, x squared in the denominator, and the only way that could be x squared in the denominator is if I can rewrite it as this being x raised to the negative 2. So you have that, and if I were to minus further, I get a higher exponent in the denominator, resulting in 4 over x squared plus 14 over x cubed. Alright, I know this was a long lesson, but this is everything we're covering currently for derivatives, so make sure you've taken clear notes. Feel free to go back through the video, see if you have questions, and otherwise, have a great day, and I will see you next class.